All right. Thanks for coming to the last lecture of this course. I hope people have found this helpful. I am going to reiterate, please fill out your MIT subject evaluation forms and the survey I put up on Piazza. Feedback's really important to me. I'd like to improve this for later iterations of the course. And the only way I can do that is if you tell me what needs to change. So last time we talked about semi-definite programming, which was a kind of one of the most general classes of problems that people solve practically. It's got good theoretical performance, and its practical performance is actually pretty good with today's solvers. Today we're going to talk about a much more difficult class of problems. So this chalk is too small. So these, what we're talking about today, are mixed integer and particularly I'm going to be focusing on Boolean, but mixed integer convex programming. So today's lecture, unlike the rest of them, is when you talk about the subject, the thing that makes the most sense to talk about is the algorithms, because it makes you appreciate it's kind of a different application of how you can use convex programming to speed up the solution time of very difficult problems. So this lecture is going to be a lot more algorithmic. And so I hope that's helpful for people, because this is the one time where it doesn't make sense to talk about the method without talking about how they're actually done. So the basic problem we're going to study, and so a lot of this stuff comes out of Boyd's branch and bound notes. And the basic problem we're going to study is we are going to look to minimize f0 xz, fi xz less than 0, cj 0, 1, j in. And then this is okay, so one of the things I mentioned at the beginning of the class is one of the reasons convex optimization kind of works is a lot of the solution techniques basically try to take these really linear steps in some feasible domain where taking a linear step is generally a good idea. If I take a linear step and both endpoints are in my feasible set, then everything in between them is also in the feasible set. So it's pretty safe to do so. By contrast here, the variables zj's are discrete. So the reason in this case, I'm going to be only talking about the Boolean case, but these lessons kind of apply any time that zj is going to take discrete values on the integers. And the difficulty here is that the steps that we have to take are very rigid, and so we can't necessarily use local information about the function to improve in as predictable of ways. So the assumption here is that the methods I'm going to describe are kind of invariant to this, but I'm just going to assume that these are convex and this is convex. These constraints are convex, and this function is convex. And the name of these problems, the abbreviation people use, is MICP, mixed integer convex programming. The mixed part comes from the fact that we have some discrete and some continuous variables. And so how many possible feasible combinations of the ZJs, just naively or generically, can we possibly have? So the answer is 2 to the n. Okay, so that is correct. And obviously this is horrible. So if n is equal to 10, this number is 1028. Solving, well, if we're talking about linear programming, solving 1024. Solving 1,024 linear programs, depending on the size, might be okay. Up to 12. This is already 32,768. That's not as good. End of the 30 is about 1 times 10 to the 9. So one of the places that these technologies get used is in things like planning bus routes or planning airplane routes and things like that. And you can imagine that there are many more than 30 routes involved in air traffic control. So in principle, this becomes very bad very quickly. Yeah?
N equals 12 doesn't yield something like 4096.
4096 will be n equals, yeah, you're probably right. I probably mistyped that in my calculator. Yeah, it would be 4096. But regardless, like these numbers shoot up very quickly. Thank you for pointing that out. I probably typed in 21. Yeah, so the unfortunate truth about these kinds of problems is these problems are, so MICP is NP hard. And so I cannot give you some magical solution that's going to do any better than brute force instantiation of all the possible feasible solutions, and you just have to run through them. But that kind of analysis, so that's the worst case analysis, right? So it's kind of from like the no free lunch theorem, is that any solution strategy I give you, you can come back to me and say, well, here's a problem instance where that strategy is horrible. But most problems, we do end up solving these MICPs for relatively large problems. And it basically comes down to most problems aren't that bad. And in the typical case, we can use kind of intermediate information about some of the solutions to help us improve on that worst case 2 to the n performance in typical cases. So the algorithm that we're going to talk about today is branch and bound. So there are more advanced versions of this algorithm. Mixed integer programming is extremely, extremely well studied. But I want to walk through this algorithm because it gives you, it's important in 2 ways. First, it's important that if you're going to use MICP solvers, that you know a little bit about how they work for like practical purposes. And it also gives you, it's a great example of how you can use convex programming and the fact that we can solve convex programs very quickly to actually help you solve some very interesting problems. So the very first thing I'm going to do, so step 1 is I'm going to solve the convex relaxation of this problem, meaning that I'm going to solve the problem minimize f0 xz subject to fi xz less than or equal to 0. Z is between 1 and 0. So my objective value here is going to be, so I'm minimizing. So the solution to this is going to give me an optimal value that is larger or smaller than the solution of that problem. Right. Smaller. So if I call this, I'm going to call this Z empty set. How do I want to say this? Okay, so P empty set star is going to be less than, we're going to call the optimal value up here P star. Okay, so P empty set star is definitely going to be less than P star. So solving this is going to give me a lower bound on my problem. Now, the thing is, I've solved this problem, I have some Z. I can use that information to actually, well, I have a Z, so why not just round it, right? And what I can do there is, so actually before I do that, what happens if when I solve this relaxation, the problem returns infeasible? Is the original MICP going to be feasible or infeasible if this is infeasible? So the answer from someone in the back is yes. If this relaxation is infeasible, well then the original one obviously is also infeasible because, well, this set contains that set. So I'm just going to assume that we have a feasible solution. So if I round my Z empty set star to Z bar star empty set, so I'm going to do this by rounding. What I can then do is I can solve this problem again using this variable right here, right? And so I can use this, solve an instance of this problem with the binaries all fixed to this value, and obtain a new solution that P empty set star. And that value, when I resolve the problem, is going to be more than, less than, equal to the original problem's P star. Answer says greater than or equal to. That is correct. So what have I done here? At step 1, I've solved the convex relaxation, and I have gotten both a lower bound and an upper bound on my solution. If those are really close together, and I'm fine with, if these are 10 to the minus 5 apart, and I'm okay with having an answer that could be as much as 10 to the minus 5 suboptimal, well, I'm done. This rounded solution is good enough for me. So this upper bound and this lower bound is really important because it's going to give us an idea of our progress along of where the optimal value of this problem could actually be. So I'm gonna get to that. So what I'm going to do, and yeah, the empty set notation is going to make sense at this next step. So what I'm going to do is, so we know that Z is some binary vector. We'll just call it that. And so what I've done is I've solved a first instance of the problem where when I say the empty set, I'm leaving all of these things blank. The next step of the algorithm, so right now what I've done is bound. The next step is I'm going to branch. So here, I'm going to declare Z1 is equal to 1. Z1 is equal to 0. And so the notation I'm going to use as I fix, and you'll see as we keep going, I'm going to solve these problems again and again. And then I'll have something like Z2 is equal to 1, Z2 is equal to 0. And so the notation I'm going to use to kind of build up the indices as I fix them is I'm going to have Z1 mean that the first index is fixed. Z0, the first index is fixed to 0. Z11 means that I have two ones, or Z10, Z01, Z00. So that's what I'm going to mean by those subscripts. Different people use different notations, but for me, I like that. So what happens at the next step? So I have an upper and a lower bound. And now I'm going to fix the first entry of my vector to be 1. So I'm going to solve the problem with, min f0xc subject to f. And then similarly, I do the same thing here, except I change the first index to 0. So when I solve this problem, I'm going to get some results. If I solve this problem, so let's assume this was feasible. What are the possible values? So I'm going to solve the relaxation and get some lower bound, right? So P1 star lower. What is the relationship to P star lower 1 relative to P star? Less than or equal to. And what's its relationship to, someone already said the answer, for the empty set star, it's going to be lower. Is that one true? So is this one actually true? What?
It might not be if P1 being equal to 0 instead of 1 gets a lower value.
So the answer is that P1, maybe the optimal solution has the vector z equals 0, 0, 0, right? Well, then fixing to 1, this is going to be, that could in principle give me a higher bound than the P star. So actually this inequality is false.
Is it supposed to be flipping those two, that P star is between those two? Or can it also be?
So yeah, so this has to creep up, but it could creep up past the optimal value. If that 1 shouldn't be there in the optimal solution, I can actually force something incorrect. But so once I fix this, I can generate a Z1 bar star, which is the rounded solution, right? Use it to solve another convex problem to obtain the optimal x for that, and that gives me some upper bound. Which is going to be less than or equal to P empty set star U. So from these two inequalities, we immediately get this following property. And the same will be true for P0. Okay, so this already tells you kind of one of the main ideas of this. By going farther and farther down this tree, every time I get to a new node, the best I can say is that the gap between a child node and its parent node must be less than or equal to. So I do want to be careful about this statement, though. Because this tree is going to have a lot of levels. And what I want to point out is that this graph tells you which ones are comparable. There's a question.
P0, there's two uppers, one of them be a lower.
Thank you. Okay, so this graph is a nice picture to keep in mind because it keeps you honest about what is actually comparable. So can I compare the value of this node to the parent? That gap between the upper and lower bounds. Do I have any guarantees about the size of this gap versus the size of that gap? Yes, I do, because there's kind of a complete directed path from this to this. So I know that this gap has to be bigger than this gap. What is not true is I cannot compare this node's gap to this node's gap. Both of these can be compared to their parents, but they cannot be compared to each other in the sense that I can't promise that this gap is going to be bigger or smaller than that gap and vice versa. I also can't compare this node to one of these guys. On the other hand, let's talk about the on the other hand, we can say one thing. I can do one thing. At the kth level of this tree, I'm going to have What I can say though is I do always have an idea of the suboptimality gap that's even better than the gap at any given node. The highest lower bound, sorry, it's the least lower bound. Right, so the lower bound that's the smallest, well, one of these trees has to be right. And so the one that gets me the closest to the bottom at the kth level, the one that is the smallest, always tells me what's the worst that could be. What's the lowest value that P star, the solution to the optimal problem, could possibly assume. Conversely, the highest upper bound tells me what is the maximal value that could possibly happen. And actually, I can probably improve this to min. Question?
Is there not an error up there with P1 star upper bound is less than or equal to P star upper bound empty set? Shouldn't it be backwards since P1 would have to be greater than?
Yes, thank you. Sorry, there are a lot of signs that flip in this lecture, so thank you for keeping me honest. Okay, so you might be wondering, okay, so we can build this tree and we're spending a lot of effort solving these intermediate convex problems. So why don't I just get to the bottom of the tree and solve everything? Well, the point is you actually don't end up having to split every node. So let's look at the possibilities of that. Largest, lower bound, smallest. Okay, so let's do this. Let's say I've expanded my tree to some level here, right? And I solve the convex relaxation. And lo and behold, we luckily get integral solution. So let's say when I fixed, so I have 3 slots. And I solved the convex relaxation of this problem, and this turns out to be 1. What happens? Well, what would happen to every child of this branch? So let's say this one's integral. If I split this and try to keep going down the tree, well, if I split and keep going down the path of the integral solution I had, well, I'm not going to improve. It's just going to be the same solution every time. If I split and go down a different path, well, I already know that the solutions it's going to give me are going to be bigger than the ones I found. So once here, don't branch. Because continuing to expand that node isn't going to give me any more information. So that means I can cut out all of the things down that branch. Okay. What happens if at some point I fix the prefix of my Boolean vector prefix implies infeasible. If the prefix, by fix it, and by prefix I mean I fix the first few to some value, if that prefix results in a branch that's infeasible at this node, what's true about everything under it? They're all infeasible because they all share the same prefix anyway. So once again, don't branch. Okay, now let's say, so at the kth level, we have that we have our best upper bound and our best lower bound. And so I'm at the kth level. I'm going to go to level k plus 1, or actually not even. I'm at the kth level. And I have some lower bound on my solution and some upper bound on my solution. Let's say that some p star lower 0, 1, k is let's say that at some node at that level, the optimal solution, the lower bound on that solution that I'm computing there, is actually bigger than the best upper bound I have. I think you can probably guess what I'm going to say. Once again, don't branch. Why not branch in this situation? Yeah, so the answer to the question was, well, at this node, I already know that my optimal solution is lower than the value of going down that branch. So there's no point in continuing down that branch. It's not going to be better. So names for nodes that you're not expanding anymore, Garobi calls them fathomed. Meaning that you've gone down the tree and you've hit the bottom already. Like, we don't have to keep going. I've already hit the bottom. So obviously, I chose an order to do this branching. You don't have to use that order. I mean, really good solvers, first off, will do this in parallel. Second, they're, sometimes picking them in order like that's a good idea. People have come up with a ton of heuristics on which leaf to go down, which thing to branch and bound, et cetera. From the no free lunch theorem, all of those are heuristics. For a given problem, there might be better branching heuristics, and your answer will always be someone will give you a counterexample where that's a bad idea. Some people actually train neural networks to decide these heuristics now, which I think is kind of cool. But because usually when you're using this, you're trying to solve the same types of problems similarly. There's a lot of research in this area. So one of the most important things in practice is, that I'll talk about in a second, is I'm having to solve a lot of convex programs. And so things such as some of the keywords you'll hear are warm starting, tight convex relaxations. I'll talk about those in a second. But yeah, so there's no way I can cover all of that in one lecture. But there's a really interesting topic. To kind of drive home the point, and at the risk of being a little bit pedantic and slow, I'm going to go through a really small, just Boolean integer example, which I wrote down here. Min 2z1. Okay, so at the very first iteration of this, I'm going to, if I solve this problem with convex relaxation of letting all of the zi's be between 0 and 1, I get a solution of minus 0.143 with a z star equal to 0.4311. Okay, so this rounds to 0, 1, 1, and this actually makes the problem infeasible. So at the first relaxation step, I got some value. That gives me a lower bound on the optimal solution. But when I rounded that solution, I got an infeasible one. Okay, so now I am going to branch. So let's do, this is just infinity. This is my, I'm using this as the lower bound and this is the upper bound. All right, so I'm going to go down the branch z0. So I'm going to set the first, I'm going to set z1 to 0. This results in an infeasible problem. Did I need to go down this branch? Because, so did I need to go down this branch? Well, when I rounded, the first index was 0. So did I, and I knew that was infeasible. So did I still need to go down the branch? Someone said yes. That is the correct answer, right? Because even though this index matched, maybe 0, 0, 0 is feasible. Turns out not to be, and so I don't need to keep going down this. Let's go down the z1 branch. So here I'm going to get z1 star equals 1, 0.2, 1, which rounds to 0, too small. Z1 star here is 1, 0.2, 1, which obviously rounds to 1, 0, 1. Just going to put that over there. So, and the values I get are 0.2 and infinity. Okay, so once again, I fixed the first entry, let these two free. Very conveniently, z3 was integral. I found some value. When I rounded, I got infeasible. So same question. Do I know that the third entry needs to be 1 in the optimal solution already? No, you do not yet know that, even though it happens to be integral. The exit condition, is if all of them are integral, then I'm done with that branch. Okay. So now let's do Z1, 0. This results in infeasible. And if I go down this branch, Z1, 1 is equal to 1, 1, 1. And the value is okay, so now I have infeasible and now I have infeasible. And this at this node now, I've got an integral solution. Do I need to keep going? Do I need to do any more branching? No, I don't, because I don't need to branch that. I don't need to branch that. This is integral, so I don't need to branch. So now I'm done. So the worst case here is I would have had to try 2 to the 3 is equal to 8 solutions. Well, here I managed to do it by solving 1, 2, 3, 4, 5 problems. That doesn't seem like a lot, but these ratios can be way, way better in some bigger problems where, you know, you have 10 to the 38 solutions and you cut it down to 10 to the 10, which still probably isn't practical, but at least you've eliminated 10 to the 20 possibilities. So there are two practical things that people study a lot in this field. Okay, so the first one is called warm starting. So when people talk about warm starting and optimization, what they're talking about is some of these algorithms, these solving algorithms, you can actually give it an initial guess, and the better that initial guess, the faster you'll solve. This is particularly important when we're going to be solving, you know, a couple hundred or a couple thousand optimization problems to solve these MICPs. Importantly, as we go down these branches, a lot of times the solutions are pretty similar, right? Every time I fix a new binary, I can, especially if, you know, I have a solution and it was 1.21, well, I know that when I round it from to 101, I know that solution is probably not going to move all that much. So being able to warm start's really important. And this is one of those places where it's important to know what kind of problem you're solving. So linear programs and QPs, we have a good handle on how to warm start. So linear programs, the simplex method is really good at warm starting. QPs, there are these things called active set methods that are also very, very useful for warm starting. On the other hand, SDP, basically everyone uses interior point. And that doesn't warm start that well. I'm not going to claim that it's impossible because I'm not an expert on warm starting these algorithms, but the kind of like common thing is, well, if you're going to be doing mixed integer stuff and you need fast performance, being able to use LPs and QPs is going to scale better because they solve faster regardless of the size. And warm starting can give you even more benefits over using something like an SDP. And so this is why, it's practical to know that, for example, I can represent the 1 norm using an LP, but if I do something like the 2 norm, well, now I'm in doing things as QPs or SOCPs or things like that. So you do want to be careful and recognize what kind of problem you're forcing the solver to use. The other practical aspect of this is what are called tight convex formulations. This is not something I can give you an insight into because they're really, really problem specific. But basically, tight formulations, you might hear this term. Approximately means convex relaxation gives integral solutions. Or approximately integral solutions and things like that. It means that as I constrain the problem, I'm converging very quickly to integer solutions. There's kind of an art to doing this, where people will add different constraints. It might be that instead of just relaxing between 0 and 1, you can give, tighter conditions that, well, I can exclude all of this convex set of solutions because of this reason and that. And there are hundreds of papers written about that kind of stuff. So the next, are there any questions? Okay, so the next example I'm going to talk about here is a canonical and very, very difficult problem that you've probably heard of called the traveling salesman. So traveling salesman is abbreviated TSP, and the idea is I have a bunch of cities, and I'm going to start at this starting city. And what I want is and so between each city, I know that there's a cost, Cij, which I'm just going to make symmetric, that's telling me how much it costs to go from city I to city J. And the goal of traveling salesman is to find a path that visits all of the cities, starting from the start and coming back to the start. So I want to visit all the cities with the least amount of cost. So you can imagine that solutions to this problem are, this problem's basically impossible to solve optimally. It's very, very difficult, especially kind of generalizations. But generalizations of this correspond to, vehicle routing. So like, how does Uber decide who to dispatch to who? Amazon delivery or anything like that. So this is a very important problem to be able to solve. So I'm going to try to tie this back into our graph search hat that we started this course on. I'm also going to assume there's a common assumption that we satisfy the triangle inequality, that the costs, there's like a good assumption for like Euclidean distances, for example. Okay, so what we're going to do is we're going to introduce the binary. Let's move that up there so I don't erase it. All right, so we're going to introduce xij equals 1 if the path I'm going to take, which we're going to call tour, connects I and j. Okay, so what's going to be the cost of my tour? Cost of the path I take. Let's start there.
You guys, is it a sum or can you just express it as transfer?
Yeah, so it is a sum, right? It's but I can just conveniently express this as C transpose X. Okay, so remembering the kind of graph flow problems I was talking about at the very beginning of class, I want to leave every city once, right? I know that I don't need to visit every city more than once in a shortest path, right? So I want to be sure that I leave every city once. This is summing over I. And I also want to enter every city once. Okay, so now I have some mixed integer, not even mixed integer, just integer program, integer program I can solve using branch and bound, using a branch and bound solver and solving a bunch of these, et cetera, et cetera.
Aren't these two constraints saying the same thing? Because you're summing over I, but the I is the first one.
Thank you. Is this a complete set of constraints describing my problem?
No, you probably want to add a constraint about the endpoint.
I want to add a constraint about the endpoint. Well, I want a complete tour, which means I want to enter and leave every node once, so it doesn't really, once you connect the edges, I can choose where to start in the tour. So that's not the problem. Okay, is this a feasible solution to that optimization problem? Some people are nodding, some people are shaking their heads.
I mean, to that optimization problem, it's not what we want.
It is a feasible solution to this one, right? I've entered and left every city, and I've connected them. So that problem is not equivalent to traveling salesman, because I don't want this. Okay. So even though I've given a formulation, I'm clearly not done. So the fix to this is, let's think about what I'm trying to fix here. So what I want is to form a complete cycle, but I don't want any subset of the vertices besides all of them to form a complete cycle. So let's let S, which I'm not calling the starting vertex, let S be some subset of the vertices of the graph I have. And so for any given subset of the vertices, right, I need to enter and leave exactly once. So this constraint's a little tricky to see, but essentially what I'm doing is I'm saying that if you give me a subset of the vertices, then there only has to be one, there has to be an entry point and exit point for all of them. Okay, so
I guess that kind of makes sense, so you can just skip between subsets, which would have been what happened without the constraint, and you'd just be going sort of separate loops with no entries and exits between them.
yeah, so the intuition here is I'm trying to exclude the possibility of letting myself have disjointed loops. If I have two loops, I need to enter and exit them. Go ahead.
Is there any way that, other than checking every subset, because for a large problem, there's a lot of subsets?
So the question right now is, well, this seems like a bad idea because how many subsets are there? How many subsets are there of the vertices? 2 to the n minus 2. Okay, so remember when I said that TSP is extremely hard? It's NP hard, actually. So there's no way you're going to do better than this. I mean, there are other formulations and things like that, but if you want a complete description of the problem, something's going to be exponential in the vertices and the edges. So you're right. This is bad. It's really, really bad. Because for big, I mean, you can imagine that Amazon's visiting hundreds of houses with one van, and they need to schedule all of these vans. They actually have a generalization of this problem of they've got multiple salesmen that need to not overlap and things like that. So yeah, that's bad. So this is where I'm going to bring up another algorithm that is extremely similar to branch and bound. This one's actually a branch and cut algorithm. So the idea here is that, well, imagine I didn't have to list these. Imagine that I just got rid of all of them, and I was actually given a solution to the problem that turned out to be a tour. Like they're called Hamiltonian cycles, these things that visit, the shortest path that visits every node. So imagine that I was actually given, I ignored those constraints and I got one. I mean, that's a feasible solution of the most relaxed version of the problem, that's clearly the optimal solution, right? Someone's shaking their head, so I'm going to be.
Right, so a feasible solution of the most relaxed form of the problem.
So the actual traveling salesman problem would have this constraint right here. What if I ignore that constraint completely? I'd have a relaxed version of the problem, but so the optimal value can only be lower, the optimal value of the actual TSP problem can only be bigger than that relaxation. But if that relaxation gives me a solution to the TSP problem, it's got to be the optimal solution.
Okay, yeah.
So the main idea behind branch and cut is basically that here. So what I'm going to do is I'm going to solve TSP without any of those subtor constraints. So I'm going to get a solution. If it's a tor, then done. 2. Okay. One of the things that's really nice about this is I'm going to get a solution. It's really easy to check whether it's if it's actually a solution to TSP or if it contains subtors. Right? So if it contains subtors, let's say it contains M subtors. Well, just by checking the solution of my problem, I've found subtors. So I've already kind of loaded them into memory and I know what they are. So now what I'm going to do is just resolve with those subtor constraints. So I'm going to redo the whole problem, resolve with all those subtor constraints kind of excluded. And I'm going to get a new problem with more subtors. But every time I do this, I'm going to be excluding more and more of the subtors, and eventually, hopefully, I get the solution faster. Because some of those other subtor constraints are not active in the actual solution.
How do you give the subtour constraint? Is it just the setup that you previously found, or like without checking the number of tours that, or like to check? I guess how do you check if it's the tour? Is it just you do it once?
So the question is, how do you check whether you had a tor? You look at your solution and you try to walk along it. If you end up back at some starting vertex without visiting everything, you know you have subtors.
Okay, so for each of these, will you do a depth first search each time to identify the number of subtours you have to your constraints?
So the question is, would you just start with a depth first search? Yeah, I mean, there are ways to check this efficiently. And I mean, then it becomes a computer programming question of how do I actually code this so that as I'm walking, I'm adding the constraints and things like that. But ultimately, just by checking the solution, I've checked a subtor that I want to exclude every time. And importantly, you might be wondering where the branch part of this comes from. Essentially, if you find multiple subtours, you don't have to exclude every one from your solution. You can exclude some or all or something in between. And doing different exclusions might get you to the answer quicker. So you can kind of parallelize this. But in general, super, super hard problem. You're not going to be able to check every solution. You're not going to be able to solve this for every instance, regardless of regardless of whatever algorithm you give. The attendance code for today is B and B, branch and bound. And that is everything I have for today. I wanted to leave time at the end for questions about the course, about anything like that. So if you guys have any residing questions about any part of the course, this lecture, now would be a good time to ask.
Can you maybe talk a little bit about lossless convexification? It is originally non-convex problem, but with some tight convex relaxation.
So the question is, can I talk about lossless convexification? So a problem that's originally non-convex, but the convex relaxation is tight. So in the very first lecture, I talked about graph search as an LP. That's an example of a problem where it's originally discrete, you solve the relaxation, and the relaxation is guaranteed to be integral. So the easiest family of problems for that, I guess the most well-known one is if I have an LP in standard form, if A and B have rational entries and C has rational entries, you can actually prove that this has a rational solution, that the solution is always going to be fractional. And in fact, if A is a property called totally unimodular, so if A is totally unimodular, then you have integral solution. Again, under the caveat that A, B, and C are all rationals. But that's probably like the biggest class I can think of offhand where a relaxation is fine. But again, every non-convex problem can be written as a convex problem. That maybe it's infinite dimensional, but there are always problems with doing that. But one of the things I said is convexity is special, but it's also not special. What's special is convexity that we can represent easily.
So you had said something about global polynomial minimization with SDP.
Mm-hmm.
What sort of applications are there to that? Because it seems like it'd be something like really hard to do.
Yeah, so the question I got is about a comment I made that you could use sums of squares and therefore SDP to do global polynomial minimization. So that's definitely true in the single variable case. So if I have a single variable polynomial, f is a polynomial here, then in the single variable case, it is true that every non-negative polynomial can be written as a sum of squares. So that's not true when you have more variables. But essentially the idea is like, say I had, actually, that's a bad picture. Say I had a polynomial, even degree, obviously, if I'm going to try to minimize it. It's going to go up and down in a bunch of places, and I want to find its minimum. Okay, so let's say this is p of x. The idea here is that, well, how can I find this minimum? If I take p of x plus some gamma, well, I can lift the polynomial up by some scalar gamma, right? And so what I can do is I can actually formulate this problem as minimize gamma subject to p of x plus gamma is more than or equal to 0. And this non-negativity is something I can write as a sum of squares condition. In the case of single variable polynomials, this is global. In the case of multivariate polynomials, it gives me a lower bound, an upper bound on the minimum value, because in higher dimensions, the sum of squares, there are other ways to write down polynomials, and so I can only really guarantee an upper bound on the minimum value. Yeah, sums of squares polynomial programming is extremely, extremely useful. All right, well, thanks everyone for coming and attending. Again, I reiterate, if you haven't filled out the feedback forms, I would really appreciate if you did. And yeah, thank you.